Rotations with quaternions. Suppose that we want to rotate a point P and a vector V with a quaternion Q, where Q is a unit quaternion representing the 3D rotation matrix R. And we want to achieve a rotation such as this, R multiplied by P and giving us P dash, and R multiplied by V giving us V dash. How can we perform this using the quaternion Q? So first we append P and V with a 0, just like this, and then we multiply P with Q as shown here. We pre-multiply it with Q and post-multiply it with the inverse of Q, the quaternion Q. And we perform the vector and point rotation exactly in the same way. Both the outputs P dash and V dash are 4D entities. Their first components would be 0. To convert them back to the 3D space, we simply drop the first component that we added. Now, we could have put 1 instead of the 0 here because it will have the same effect, since quaternions cannot be used for scaling or translation. So remember, quaternions cannot be used for scaling or translation. Now, one of the advantages of quaternions is that they can be used for animation, and to animate we would need to interpolate the quaternions. There are two ways of interpolating quaternions. One method is called LERP, that is the linear interpolation, and the second method is called SLURP, which is spherical linear interpolation. So linear interpolation is simply moving from Q0 to Q1 in linear steps, whereas SLURP, spherical linear interpolation, is analogous to moving on this circle, or in 3D on a sphere, and the intermediate points would be given by this equation, where theta is the angle of the total rotation and t are time steps that go from 0 to 1. So there will be decimal values between 0 and 1. Linear interpolation is simple. Now notice that because here t is subtracted from 1 and t is multiplied with 1, they both add up to be equal to 1. That is, the weight of Q0 and Q1 add up to be 1, which means that starting with t is equal to 0, you will have Q0, and t is equal to 1. This will go to 0 and you will have only Q1 left. But this is not the case in SLURP. You will have to make the values of SLURP as unit norm once you have interpolated. It is written here, so normalization is required in SLURP, and these red parts are basically the weights, and because that the normalization is required because they do not add up to be equal to 1 as in the case of linear interpolation. So the aim in SLURP is that we want to achieve the shortest trajectory, the geodesic trajectory that brings the initial orientation Q0 of the object to its final orientation Q1. Mathematically, we find the difference between two to be equal to delta Q, which changes Q0 to Q1, and delta Q, the value of delta Q would be Q1 multiplied by Q0 inverse. Then at each step t, where t is in between 0 and 1, the interpolated quaternion is computed as delta t raised to the power t multiplied by Q0. Now, SLURP gives smoother intermediate steps. However, you need more computations to calculate SLURP based interpolations compared to the simple linear interpolations, and that's the trade-off you want to achieve. And you really have to implement your animations and see if you do notice any advantage by using SLURP. Otherwise, you can fall back to the simple linear interpolation, which is faster. Unit quaternion is not a unique representation. That is, there is not a single way of representing the same rotation. There are actually two ways. So Q is equal to AV, where A is the scalar and V is the vector. can also be represented, and A is the angle over here and V is the the axis along which the rotation happens. This can also be represented with minus A and minus V, which simply means that if you were to perform 160-degree rotation in one direction, you can perform 200 degrees rotation in the opposite direction, and they will both have exactly the same effect. To avoid interpolating along longer paths, we change the sign of the quaternion so that the first component is always positive. The first component of the quaternion is always positive. This will ensure that we are rotating along the smaller angle and not along the larger angle. Inside your graphics software or the graphics pipeline, we need rotation matrices to perform the rotations. Quaternions are only used as intermediate representations to interpolate them to achieve smoother animations. And once you have interpolated the quaternions, you will have to convert them back to rotation matrices. So one method is called Rodriguez rotation formula, where you can convert a quaternion taking its V and theta values back to a rotation matrix. So where I denotes a 3x3 identity matrix. So I over here in these formulas denote an identity matrix of dimension 3x3. Theta can be obtained from the first component of Q by setting first taking an arc cos of A and multiplying it with 2. Skew V denotes the skew symmetric matrix composed from the elements of V. So here we are taking the skew of the V, the second component of the quaternion, and skew V would be actually equal to if the value of V was given by V1, V2, V3, skew V would be represented with this matrix. In OpenGL, quaternions are not directly supported, so you'll have to implement them yourself. So what steps do we need to perform? First, we do all the rotation interpolation between the frames using unit quaternions. That is, first we convert all the rotation matrices to quaternions. So rotations to quaternions, quaternions to interpolation, and interpolating quaternions will give us many quaternions, Q1, Q2, Q3, and then we convert those quaternions back to rotation matrices and pass them through our pipeline by giving them to the shaders. We can also use dual quaternions instead. Dual quaternions have recently been used for better blending by representing combined rotations and translations. As far as your unit is concerned, they are not included. You can read about them more here. So in summary, to generate smooth animation, we do the following steps. We define the pose, orientation, rotation, and position of each object in keyframes. So we define the poses of the objects in keyframes only. And then we have two options. Option one is, which is the preferred option. We try to use quaternions to represent rotations to avoid gimbal lock, interpolate quaternions to get rotations for the in-between frames, and we get the resultant rotation matrices for these frames by converting the quaternions back to rotation matrices. In option 2, which is not the preferred option, we try to avoid gimbal lock by changing the order of applying the roll, pitch, and yaw in the rotation. And once we have interpolated the rotation angles, we derive the rotation matrices and apply them to achieve smooth animation. We can also combine the rotation with scaling and translation to get the resultant transformation matrices for the vertex shader.